Swayam Prabha. Digital India. Educated India.
Welcome everybody to NMR Spectroscopy. We are going to work out a whole bunch of problems, as you can see. Well, why do I have 4 of them out here? Because they all share the same molecular formula. That means you have different structures for the same molecular formula, which is pretty much the definition of isomers. And so we have 4 isomers with this molecular formula, and the problem says that they are esters. So we have that much of information to start with. Okay, so let's look at each one of these separately, because even if you have isomers, you know, they can have completely different backbones. So that's why you have 4 different structures. We have 2 oxygens here, and so that we have to take into consideration when we solve the problem. The heteroatoms are very important. All right, let's do the omega first, which is the IHD, and that is going to be 2n plus 2, n being the number of carbons minus m over 2. Oxygens, you don't add or subtract hydrogen, so we just leave that as the number of hydrogens. So n is going to be 10, n, number of carbons, in this case it's 10, m is number of hydrogens, in this case it's 12. Oxygens we don't add or subtract, so that's going to be 22 minus 12 over 2, and that is going to be 5. Okay, so that's a lot. Well, last time we looked at something that had a lot of unsaturation, and we said that if you had something around 7, and look at this, they all have a peak around 7, then we should think about benzene. So 4 of this would be for benzene, and then we would have this has an IHD of 4. Therefore, in addition to a benzene, you could have another ring or a double bond. So we have that much information here, and since they're telling us this is an ester, esters would have a C double bond O, and so that's RCO2R is an ester, and this is going to be written out as a carbonyl. So that kind of accounts for the other unsaturation. All right, so we've figured out where all our omegas went. Okay, let's look at each of these spectra and put a structure together. Now, if you have a benzene and you have 2 oxygens, there are certain deltas that you have to look for, or chemical shifts. And I'm just going to briefly talk about chemical shifts here, since we didn't mention it before. The chemical shifts are based on the amount of shielding around the hydrogen. So a hydrogen has the maximum number of electrons around it when you have TMS, which is tetramethylsilane. Compared to those hydrogens, everything else has less electron density around it. The hydrogen density gets depleted when you have electron withdrawing groups attached to the carbon bearing the hydrogen. So the more electron negative the atom is, in this case we have oxygens, you would have very de-shielded protons. And benzene also, if you have protons on benzene, we said those were around 7. So we have some very de-shielding environments here. Let's just take a walk through this chart, shall we? So here's an alkyl with a CH3, and those are some of the most shielded protons. That's 0.8 to 1. Okay, And if you have this is a primary, if you have secondary, RCH2R, that goes up and to 1.2 to 1.4. If you have a tertiary, it goes 1.4 to 1.7. Okay, so when you go from primary, secondary to tertiary, your de-shielding increases. And here, when you go from tertiary to primary, your shielding increases. Now, after that, after about 2, then you typically have electron withdrawing groups on there. Exception is when you have sp and sp2 carbons. Okay, this is all for sp3 carbons. If you have a double bond sp2, these hydrogens are typically about 4.6 to 5. And if you have a double bond and you have a hydrogen like this, it can go to 5.2, 5.7. So you can go up to 6.5 sometimes for vinylic hydrogens. So those are very, very de-shielded. So sp3s are the most shielded. sp2s are the most de-shielded. In between, you can have your triple bond CH, which is about 2.5 to 3.1. Right, so this is a little. It doesn't follow the typical sp3, sp2, sp rule. It's sp3 is the most shielded, then sp and sp2 is the most de-shielded. Now, what about aromatic hydrocarbons? And those sp2s are even more de-shielded. These are between 6 and 9.5, so they're very de-shielded. Now, what else can you have on these carbons? Typically, you have oxygens, nitrogens, for the most part. Okay, you can have sulfurs and phosphorus, but it's not on this chart. Let's look at some of them. If you have a carbonyl, you're not going to be showing up on a proton NMR. But the neighboring carbon hydrogens, so this is the alpha position, these CHs are going to be between 2.1 to 2.6. All right, so these are de-shielded because of the carbonyl. If you have a benzene and you have a CH next to the benzene, those will be between 2.2 to 2.5. So these are also de-shielded because of the benzene here. So going back to oxygens here, you can have next to a carbonyl, you can have it right next to a oxygen itself. So if you have an alcohol, or CH2OH, these hydrogens can be somewhere between 3.3 to 4. Okay, so that's very de-shielded because this is directly connected to an oxygen, which is different from being connected to a carbonyl here. The carbonyl has 2 carbons, in fact, in between the hydrogen and the oxygen. Here, there's only 1 carbon between the oxygen and the hydrogen. So therefore, when you're directly connected to the oxygen, you're going a lot higher in terms of ppm, almost more than a delta higher. Okay. Now, you could have a proton that is right on the carbonyl. So if you have a carbonyl and this is an aldehyde, if you have an aldehyde hydrogen, now you're going to be way more de-shielded than any of this. It's 9.5 to 10.5. So that's really very de-shielded. The only proton that's more de-shielded than a aldehyde is a carboxylic acid. And so that is going to be, because of the resonance and all of the other effects, these are going to be 10 to 13. So now NMR scale is 0 to 10. So how does it draw a 12, let's say? What it does is it puts an inset. So they'll have an NMR, and then you see a small box inset, and then there it's going to say, well, 12 ppm or whatever, there is a peak. All right, so it's off the scale, literally. Okay, that's why we have to put it in a separate box. You can have other things too. For example, halogens. Halogens, if you have, let's say, RCH2I, that's 3.1 to 3.3, typically above 3, and below 4, typically for halogens, are CH2Br 3.4 to 3.6, and then it gets higher when you get more electronegative, and chlorine's more electronegative than bromine, bromine's more electronegative than iodine. So that trend, really makes sense. So 3.6 to 3.8 when you have a CH2 with a chlorine. Okay, we don't have fluorine here, and fluorine spectra can be complicated because fluorine also has an odd number of nucleons, so we're not going to get into that here. Okay, so you can see that these are really the trends. The more electronegative, the more de-shielding, and higher the delta value, and you kind of saw that. Now, there are two types of protons in an NMR which have a very wide range for the delta, and they can appear anywhere, and typically they are broad peaks, and we saw some of them earlier. So if you have an amine, RNH2, it's anywhere between 1 and 5. And if you have a OH, it can be anywhere between 0.5 and 6. So these are two kind of wild cards. They can pop up anywhere between, this region and this region. And typically they're broad, so it's easy to identify them. Even the carboxylic acid hydrogen, anything on an OH or NH, typically are broad peaks, but you can get them to become narrow by changing the dilution, purity, and so on. So this is just a walk through this chart here. And so how do we apply that to this? We have to really look at the ppm values here. So this is next to a 4. So chances are that is directly next to an oxygen. Now over here you can see these are next to 3s. So that could be next to like a benzene and a carbonyl. You see. Now over here you're seeing 1 on 4, which is probably going to be right next to an oxygen. And here something at 3 that could be next to a carbonyl or benzene and so on. Here something at 2. When you have something at 2, like acetone, it's typically a carbonyl next to a CH3 or a CH proton. Okay, these are typically at 2 or 2.1. So when you see 2.1, think acetone, think CH right next to a carbonyl, right? And you see that here too. So you know that these protons are typically right next to a carbonyl. So all the 7s are going to be protons on the benzene. So that's really nice that you can kind of isolate them and say, okay, we have a benzene. What else do we have? And then we can take benzene out, which is going to be C6 and probably H5 or 4, depending on the number of substituents. And then you can come up with a structure for the other 4 carbons. We already know that we have a carbonyl, so the rest is going to be saturated, like CH2s and CH3s, or CHs that are all sp3s. So we have a lot of information just by looking at the chart. So even if you don't have an IR, you can look at this chart and try to figure out what are the possible functional groups. Now, and if you had an IR, obviously that's going to be, very valuable added information. So all 4 of them would have very similar infrareds, which is why you really cannot tell isomers apart based on infrared spectra, because all 4 of these have a carbonyl and a benzene and an ester group, COO group. They're pretty much going to look the same. So we have to then look at the NMR to find out which isomer is represented by each one of these. There may be more isomers. We're just going to only look at 4. There are definitely more isomers than that. All right, so let's compile this data here. AB's 4 peaks here, A, B, C, D, and the delta ppm for this is about 1.2. I'm doing kind of an approximation. I'm not going, you can go to 2 decimals, but I'm just, not doing that here. About 3.7. This is about 4.1, and here we have something at 7.2, a typical benzoic hydrogen. right? Let's do the multiplicity next. This is a triplet, singlet, quartet, and a multiplet. So triplet, singlet, quartet, and multiplet. Now over here, this multiplet is kind of a 2 to 3, and the 3 is more shielded and the 2 is more de-shielded. So that kind of would help us to figure out the substitution pattern to some extent. Number of hydrogens. So over here, we do have to measure the distances here and then put them in here and see how it is. Okay, so let's do the heights here with a ruler. So grab our centimeter ruler and see the ratio here, the height ratio for this. This is 2, this is 3. This is 2, 2, and 3. So let's see. So A has 3 hydrogens, this has got 2, this has got 2, and this has a 2 to 3 ratio, 5 hydrogens underneath the benzylic hydrogen. So that means it is mono-substituted. It's just got one arm to hold somebody. Now, this is like the most valuable information of all of this. Multiplicity can tell you how many hydrogens are neighbors. Okay? Neighbors. Not on the same hydrogen, but on the neighboring hydrogens. That's really, really important. So n plus 1 is equal to a triplet. Triplet means there's 3, so n is 2. That means this guy, A, has 3 hydrogens here, and the neighbor has 2. Over here, this is a singlet, so therefore n plus 1 is going to be 1, n is 0. So this guy is in a unique environment where it has no neighboring hydrogens. Okay. C is going to be n plus 1 is a quartet, that's 4, so n is 3. So this guy has 3 hydrogens next door. Okay, I think we've seen quartets, remember? So recall what happens when you have quartets. And this is a multiplet, and so this is going to be, 5 hydrogens. All right. So let's look at this. Do you see any patterns? That's what we need to check for. We've been looking at patterns, and if you have a singlet, that means you could have a Y is something that doesn't have hydrogens, and you can have a CH3, or you could have a T-butyl group, 9 hydrogens here that have no neighboring hydrogen. Okay, if you have a triplet quartet, and you've seen this all the time, I should say quartet would be usually the D-shielded. When you see this pair, you should always remember ethyl. That's right. So this is going to be your quartet triplet. Quartet is typically next to something here that doesn't have hydrogens, and this would be more shielded than this. Now, doublet septet, and that is typically unique for isopropyl groups. We've also seen quite often doublet quartets, and that's usually when you have a CH next to a CH3 and you have different groups here. I'm not putting X because X usually means halogens, and here it could be anything else. We also saw that if you had a long chain CH3, CH2, CH2, and a Y here, this has a unique splitting pattern, triplet, triplet, and sextet for the middle. So we've seen these patterns over and over again. And so that's something to look for when you're doing the spectra. What do we see here? Well, triplet quartet. So we know there is an ethyl. So when you're solving this, we have to look for patterns. Let's put the pieces together. We know we have a benzene, and since you have 5 hydrogens, according to the integration on the benzene, you only have 1 substitute. It's mono-substituted. And we have 3 that's shielded, two d-shielded, and you know that this is going to then be an electron donating group, and we saw that trend as well. Because ortho and para would be more shielded than the meta. Meta's d-shielded. So you have 2 protons that are d-shielded and 3 protons that are shielded. So that's an electron donating group. Therefore, you would expect to have a C double bond O carbonyl group because it says there's an ester. And you, according to this carbonyl would be an electron withdrawing group, and this is not attached to a benzene. That's the information that we know. Now, on your ethyl, if you take your ethyl group here, your quartet is on 4. And we said for 4, it's right next to an oxygen. So you have an oxygen with a CH2, and then that CH2 has to be next to a CH3 to get you a quartet triplet. So these are the 3 things that we already know are in the benzene ring. But that still doesn't account for all of the carbons because we have 10 carbons. So you have 6, 7, 8, 9. What about the other one? Well, if you look at this, there's a singlet with 2 hydrogens. And where is it? It's on 3.7. So you have a CH2 here, and that's very d-shielded at 3.7. If it is a singlet, it means these groups that are attached to it don't have hydrogens on the carbon that's immediately next to it. Okay. Now over here, this is your quartet triplet, and here's your multiplet. Let's put a structure together considering all of these. So we know we have a benzene. If it's an ester, the O has to be next to a carbonyl. And here's your CH2, CH3. Is this correct? Obviously, we haven't accounted for the singlet. Where can we put the singlet? Can we put it anywhere here? Obviously not, because this is monosubstituted. We cannot put it here or here because then the multiplicity will change. If you put it here, then it's not an ester. There's only one possibility for this CH2, and that is to put it right here. So now this is not correct. Let's correct that structure and draw it out. So putting all that information together, you would get a benzene with a CH2 next to it. That would be your singlet. And that is connected to a carbonyl here. And this is then directly connected to a CH2, CH3. So that would account for all of the things that you see in the spectra. All right, let's keep going, guys, and see what could be a possible isomeric structure for this one. Let's tabulate the data here. A, B, C, D. And here too, you're seeing a very similar pattern to this. I would put DE here. We have A, B, C, D, E. And A is about 2.7. B is at 3. And C is at 3.7. And E and D are at 7.2. Okay, so let's look at this and see how we can figure it out from the multiplicity. Triplet, triplet, singlet, and here this is more like a 2 to 3 here. Multiplet, multiplet, 2 to 3, and we saw that before. Let's look at the number of hydrogens here. This is about 2, 2, and this is 3, 5. So this is 2, 2, 3, and this is going to be a 2 to 3 or 5 over here. Next thing is n plus 1. How many neighboring hydrogens are there processing around this hydrogen? So triplet, that means n plus 1 is 3, that n is 2. So these two hydrogens have two neighbors. And it would be the exact same thing for this, because they are like twins, two pairs of triplet. Now on C, you would have a singlet, and so therefore n plus 1 is 1, n is 0. So this proton underneath here, they don't have any neighbors. Okay, they're all by themselves. Pretty happy, I'm sure. And this is a multiplet. Okay, so you have 5 hydrogens here. All right, let's try to figure out some patterns here. Singlet, 3 hydrogens. That's a methyl group. So you have 2 protons here underneath this, and they have 2 neighbors. You have 2 protons here, and they have 2 neighbors. Well, what are the chances of, them being right next to each other? So CH2 next to a CH2. Maybe we should add that to our list here. Triplet. Triplet means you have 2 CH2 right next to each other, and you have nothing or no hydrogens on the immediate carbons next to them. They're kind of isolated, CH2 groups. Let's put these all together. We have a benzene. We already have 5 protons. Therefore, we know that the benzene has got only 1 substituent. And here the 3 protons are shielded, 2 de-shielded, which means you have an electron donating group right next to it, like an alkyl group. So here 3.7 kind of de-shielded. We have 3 hydrogens with no neighbors. So we have a CH3 and there's no neighboring hydrogens. So we have kind of figured out all of the parts. And we know that it's an ester, so we got to have a COO group. It's kind of a lot easier to get the pieces and then put them together, rather than trying to do it all one shot. Because now we can take our time, look at the chart, and see where should it be if it had a delta of, whatever these values are. 7.2, definitely those hydrogens are on benzene. And 3.7, probably next to an oxygen. 3.7, most de-shielded proton here on the alkyl. So therefore, you know that that's next to an oxygen. Since this is an ester, this oxygen would be next to a carbonyl. Because this is delta 3.7, we have absolutely no doubt that that is connected directly to an oxygen. So we have this much. Now, this is a mono-substituted benzene, so you can only have one arm on the benzene holding this. Now, if it was directly connected over here, well, what about these protons then? We got to put them somewhere. And where can we put them? We can put them right in between. So here's our CH2s connected directly to the benzene. And therefore, you can see this is probably your 2.7 next to the benzene. This is your 3.0 next to the carbonyl over here. 3.7 next to your oxygen. So that's going to be our structure. Okay. All right. All right. Let's move on to these guys now. What do we have? Let's label the peaks here. The peaks here, starting from the most shielded and going downfield here, A, B, C, D. And over here we have a doublet at 1.6 around. We have a singlet at 2.1. We have a quartet at about 5.9. It's very, very de-shielded, almost in the vinylic section. And we have a benzene that has a multiplet, and this one's kind of hard to figure out. There isn't like 2 nice little lumps. They're all lumped up together, and that might, you see that a lot with mono-substituted benzene. So let's say this is at 7.2 multiplet. All right. So let's look at the number of hydrogens. Let's get our ruler out and let's look at this. So this is 3, 3, 1, and 5. All right, works out really nicely because that is the ratio of the protons. We know we have 12 protons. So if you have 3, 3, 1, and 5, that will add up to 12. It's perfect. All right, so let's look at the multiplicity and see how many neighbors each one of these hydrogens has. All right, so here's a doublet. N plus 1 is 2 for a doublet. So singlet is 1, doublet 2, triplet 3, quartet 4, quintet 5, and so on. Okay, sextet 6, septet 7, octet 8. And beyond that, it's really a multiplet. All right, so over here again, singlet n plus 1 is 1. So therefore, n is 0. Here, n is 1. Over here, quartet, that's 4. N plus 1 is 4. N is going to be 3. That's, 3 hydrogens under this quartet. And multiplet 5, okay, on the benzene. So probably mono-substituted. All right, let's look at this again. So here is a doublet and singlet and quartet. Now the singlet has 3 hydrogens and no neighbors, which means the singlet is just a methyl group and it's in an environment where there are no neighboring hydrogens. So it could be on a carbonyl, it could be on a benzene, it could be next to an oxygen, and there are no hydrogens on the neighboring carbon. A and C, where do they go together? Let's look at that. Doublet, quartet, 1 to 3. Where did we see that before? Doublet, quartet, 1 to 3. Okay, so you are a doublet because your neighbor has only 1 proton, and the quartet because your neighbor has 3 protons. So these two go together, and that is going to be a doublet quartet. So here is a doublet quartet. So this is X and Y, Z and Y that don't have neighboring hydrogens. This would be your quartet. 3 plus 1 is 4. This is your quartet. And there's only 1 hydrogen here. 1 plus 1 is 2, doublet. So we have a beautiful doublet quartet and a singlet, which simplifies it a lot. And what do we know about this? 7.2. That's your benzene. All right. Let's put them all together now. We know there are 5 hydrogens on the benzene. Therefore, it is mono-substituted. There's nobody else there except these protons. All right. So we know we have a benzene, we have a methyl, and we have a CH3CH. What else do we have? We do have a carbonyl because they're telling us that this is an ester. Okay. All right, next thing, where do we put these groups? Let's look at the delta values. 1.6 and 5.9. So one is very shielded and one is very de-shielded, doublet quartet. So, well, the most de-shielding part of the molecule is the oxygen. Oxygen, putting it on the oxygen typically is more than about 3.5 and above, depending on what else is there. And this is about in the 2 to 3 range. Same here. This is also around, 2 to 3, depending on what else is on there. All right. So therefore, the only place that you can put that is here. Okay. So your quartet, which is this carbon CH, should go over here. All right. So that much we have figured out from the delta value. So we have a COO, and our quartet should go there. So we have a CH and CH3. So this is next to 1.6 delta, and therefore we know this quartet is very shielded because we know primary alkyl groups are the most shielded, and this is a primary. So therefore it makes sense to put it at delta 1.6. This is the most de-shielded, so it's got to be next to the oxygen, which is the most de-shielding group. All right, what else do we have? Well, we have a methyl and we have a benzene. We have choices. We can either put the methyl here and the benzene here, or the benzene here and the methyl here. Now, if you put a methyl here, you know that this is going to be a septet, and we don't see a septet here. Therefore, the methyl does not go here. The methyl, which is at 2.1, and 2.1 is like perfect for sitting next to a carbonyl, like in an acetone. So that's perfect over there. So there's only one choice for a group here, because we know this has got only 3 bonds and it needs another one, and that is a benzene right here. All right, so we're done with 3 of these. Let's do our 4th isomer here. Again, we have only 4 peaks here. Let's label them and put them over here, A, B, C, D. Let's do the delta, 2.1, 3.0, 4.2, and 7.2. And we've been seeing this 7.2 over and over again, so you have a really good idea now what that could be. Let's look at the multiplicity. This is a singlet. This is going to be a triplet, and a multiplet. Over here you have 2 multiplets, and that's in a 2 to 3 range. One looks like a doublet of a doublet, but I'm just going to write multiplet here, and 2 to 3. 3 in the D-shielded, 2 in the shielded, so that gives that away for the substitution pattern. All right, number of hydrogens. Pick up your ruler, go over here, and let's look at this. This is going to be 3, 2, 2, 3, 2, and 5, that is. All right, so that's 5 here in a 2 to 3 ratio. There's 3, 2, 2. So that's 12 hydrogens, and we don't have to do anything else about it. It's just perfectly, in the ratio. All right, so let's look at the neighbors. Neighbors tell us everything, right, about you. So here's your singlet. N plus 1 is 1 for a singlet. N is 0. So there's a singlet, 3 hydrogens, no neighbors. You know what that is. Again, guys, before we start working this out on the board, you got to get that notepad and work all of these out on your own before we do this. I think we said that at the very beginning. I hope you're following along, because if you're just going to watch me, you're not going to get anything out of this, because the minute this video is down, you'd forget all about it. Okay, so do it on your own first. So here's a triplet. Triplet is 3, so N plus 1 is a 3, N is a 2, N plus 1 is a 3, N is 2. So both these have 2 hydrogens here, and they also have 2 hydrogens as neighbors, and here's a 5 multiplet on a benzene. So here we have 3 shielded, 2 de-shielded. So therefore, we already looked at this. When you have a benzene here, you are going to have a substitution pattern where you have 3 hydrogens that are shielded. That means they have an electron donating group here, which means when your electrons go in, the resonance makes these 3 carbons, ortho and para, more shielded, because that's where your electrons land in your resonance structures. And the meta is going to be de-shielded. So you have 2 meta protons, and you have 3 ortho para protons, which are kind of in the same region. 2 to 3. That means it's a mono-substituted with an electron donating group. What else do we know? Let's take A, singlet 3 hydrogens. You've seen that. That's a methyl group, and it's at 2.1, which means we know it's not directly connected to an oxygen. It could be next to a carbonyl, or it could be next to a benzene. So CH3, I'll put a Y. Okay, it could be carbonyl or benzene, but it's not connected to an oxygen, because then that would make it very much more de-shielded. Now this is 4.2. This would be a good candidate here for being connected directly to the oxygen. And this is 3.0. So of all of this alkyl groups, this is the most d-shielded. Put that on the most electronegative atom, which in this case is your oxygen. And we have 2 hydrogens with 2 neighbors. 2 hydrogens with 2 neighbors. We saw that before. Triplet, triplet. There you go. Triplet, triplet. So these 2 are going to be your neighbors. And they have a oxygen on one of them. So C, these are your C protons. And these are your B protons. And there is something here, either a benzene or a carbonyl, that does not have hydrogens. Let's put them all together, guys. We know it's an ester, so we have a carboxylate here. So let's put the structure together. A benzene ring that's mono-substituted. Then we have a methyl group, and this methyl group should be at the very end. It's not connected to an oxygen. Chances are it's connected to a carbonyl. It's 2.1 around, so it's like acetone. So this A is probably right next to a carbonyl, which means you have to have an oxygen connected directly to it because it's a carboxylate group of the ester. And what else do we have then that we haven't put in already? We have our triplet CH2, CH2. We cannot put it here. We cannot put it here. There's only one spot for that, and that's right here. And we already mentioned that this is the more d-shielded one, and so that would be your C protons, triplet, and these then would be your B protons. All right, so that kind of tells you how important NMR spectroscopy is for figuring out the exact backbone of each of these molecules and come up with a structure that is just unique for that isomer. We couldn't have done this with just IR or mass spec. The neighboring information here, N, is vital to figure out the structures. All right, if you have any questions, don't hesitate to ask me, and well, see you soon. Bye. Okay, that's done.